Tomorrow we start at 9, so for today I did an exception. There is an interference, perhaps with Jason. I don't know. Okay. So today we have a big pleasure to have Jason HARTLINE with us. So Jason is one of the leader of the economics and computation community, and I think one of the founder. At least he was in the first edition, I think, of this event. He will give more precision about it. So the economics and economic computation group is a very active group between game theory, let's say, economics and computer science. And I wanted the PhD program of the center, of the game theory center. I'm sorry about this. I have no clue how to fix it, of this interference. Perhaps you can close your... you did? Okay. And perhaps this one is... No? Okay. So, is it better? It's better. Good. So the economics and computation. So I use the PhD program of game theory here at this, in Morocco. The name of the program is Game Theory in Mathematics, Economics and Computation, and I wanted to have this economics and computation as a sign that we would like to have this represented in our training of the student. Of course, we are going to do a lot of math because we believe that mathematics and applied mathematics is fundamental. And we cannot do good research if you don't have a very good math training. But then, once we have this math training, we want to use it to solve problems. And sometimes the problems you want to solve cannot be computed using exact solutions. We need to approximate. We need to have algorithms. We need to study the complexity of these algorithms. And this is why it's important to have this computation aspect. So Jason did his PhD in Washington. I'm sure that when he started, it was really the beginning of this field, which is now a very, I think many of the new game theorists, let's say, the new generation of game theorists today are coming from this community, while when I was student, when I did my PhD, it was mostly economics and mathematics. So there was no computer science doing game theory when I started. And I got my position at the CNRS in France in computer science, and I was the first. And it was a surprise for everybody that I got a position in computer science while I was trained in applied math. Because in the CNRS in France, the CNRS is the Centre National de la Recherche Scientifique. This is where I spent more than 20 years in my life. So the CNRS in France, they took the first game theories in mathematics only a few years ago. So in math, they usually take only people doing pure math and PDEs. And now that we start to have people doing differential game, and in particular mean field games, which appears to be much more general than any equation you might find in math. That's why they start hiring people doing game theory. Economics, of course, it's already because of so many Nobel Prizes in economics. You can fix this interference, perhaps. Perhaps someone from can fix the interference. On a une interférence. Peut-être quelqu'un peut venir pour fixer l'interférence quand on parle dans le micro. Okay, so he did this. I'm speaking about game theory in general because I think I want to emphasize that what the center is doing is really game theory, but all aspects of game theory, technical aspects. So we don't, for the moment, we are not open yet, but we want to be open also to other applications of game theory, in particular international relations, political economy, and things like that. But this is something we will do in the future. We should start with what we can do and we want to do and we know how to do. So we cannot do everything. So coming back to Jason, after his PhD, he was in Carnegie Mellon doing a postdoc. Then he was at Microsoft. Then he joined Northwestern University, and I think this is where you met both of you. And even before, perhaps in Microsoft already, I don't know. And since then, Jason becomes one of the leaders of the field and full professor at Northwestern University. He has an amazing number of PhD students, postdocs, and is also extremely what I like about Jason is that he's really active in the not only for himself and the not Western, but also all the community. For example, you can find all job markets candidates, in the markets in this field. So there is a summary of all the candidates. So he may say a word about it. So if you want to hire a candidate, then he has a list of all candidates on the market doing economics and computation, for example. He founded the society. So when the COVID was there, at some moment we wanted to have conferences, and he built a virtual. Remember the name? Virtual chair. Yeah, with Nicole. That's okay. Now I understand the connection between you two. Okay. So you should add this in the game that you play all together. So they develop a very amazing tool to do conferences with avatar and moving and rooms. It's really amazing things that they did. So it's beyond game theory and beyond mathematics. It's really solving real life problems, programming. So this is something else. This is entrepreneuriat, and that's something also where Jason is amazing. So Jason is also teaching in the PhD program. So he's giving a lecture next week. So next week in the program, one week it will be about his field, which is approximate mechanism design. So how to design good mechanisms and approximate solutions of these mechanisms, market mechanisms, in particular auctions. So we have lots of amazing number of papers on auctions, collusion in auctions, and other stuff like that. Online auctions, online decision making. So he has many. It's next week here. Okay. Yeah. You can. If you are able to stay, then I will try to make sure that you can at least follow this course. If some of you can stay, but you should cover your stay, okay? Because I already ruined our department. You don't know it, but I pay for your rooms here. It's not free. Nothing is free. Your transfer is not free. Your food is not free. Everything is paid. Okay, bye. So now, okay. So even when the hat is not free, that's why I wanted to put your hat, all of you. Okay. So now I give the floor to Jason. Even Jason is not free. Yeah.
Oh, wow. That's an introduction. Okay, cool. So our lecture today is on the theoretical foundations of information elicitation. I've got a list of topics here that we're gonna go over. So we're gonna start sort of at the beginning with decision problems and how one should make decisions under uncertainty. Then we'll talk about valuing information. Valuing information is going to come up repeatedly, I think, in several of the lectures, and we'll see different ways of valuing information, which will be useful in different contexts. But I'll give one that's coming from thinking about decision problems. I'm then going to introduce proper scoring rules, which come from the literature in statistics about evaluating probabilistic forecasts. And so this is a very old literature. And then we'll look at a special case of proper scoring rules where we're trying to elicit the mean of the distribution instead of the full distribution. We'll give characterizations of what proper scoring rules look like for eliciting the mean or eliciting the full distribution. We'll talk about optimizing scoring rules. This I think it's sort of the main dish of today's lecture is going to be a long segment on how you optimize proper scoring rules. And one of the things that really surprised me is that until recently, there wasn't a literature on optimizing scoring rules. The literature mostly talked about what made scoring rules proper, but not what made them good. And as Rita mentioned, my background is in mechanism design. Mechanism design looks at how you make rules so that when people act strategically, good things happen. And scoring rules are a mechanism where you're worried about the forecaster reporting their beliefs, acting strategically. But in mechanism design, we would never be happy if we just said, oh, it's an incentive-compatible mechanism, right? Because doing nothing is also an incentive-compatible mechanism. We also maybe want to allocate resources in an efficient way, right? And so we would never consider mechanism design without optimization. And it's sort of strange that the literature on proper scoring rules considered only incentive compatibility, which is the same as properness, without ever asking, well, amongst the proper rules, which ones are good for various tasks. And so we'll look at this, we'll really have a big focus here, and I think this is really the new component of what we're going to be talking about today. Okay, and then we're going to close out with a really interesting topic, I think, which is elicitable properties. So the mean of a distribution is a statistic. So here we're trying to elicit not the full distribution. We don't want someone to report the probability of every single outcome. We want them just to report a statistic about the distribution, which is the mean. And so there are other properties of distributions we might care about eliciting, like the variance, like various moments of the distribution, like the mode. It turns out not all of these statistics are directly elicitable. Okay, meaning there do not exist proper scoring rules for eliciting some statistics of distributions directly. Okay, so we'll talk about that at the end. All right, that's my plan. As we saw yesterday, this goes as best as possible if you guys interrupt with questions or comments throughout. So please chime in when you have a question or comment. Okay, so I want to start out by talking about decision problems, where we're thinking about making decisions under uncertainty. And so we're going to have the following model. We'll have a state y, which is going to be payoff relevant. We'll have a signal x coming from some signal space calligraphic x. Our decision maker is going to want to take an action. A. And there's going to be a joint distribution over the signals and the states. Oh, whoops. Okay, so there's a joint distribution I'll call pi over the signals in the state. Okay, and so the idea is our decision maker is going to observe the signal. The decision maker is going to understand that the signal is going to be correlated with the state according to distribution pi, which means that seeing the signal tells the decision maker something about the state. Okay, the decision maker is going to update their belief about what the distribution of the state is, and then try to make a good decision according to that updated belief. Okay, and so their payoff, I'll denote by U of A and Y. Okay, so if they make action A in state Y, they get the payoff capital U of A and Y. Okay, and so as you can see, when they see their signal, they're going to want to update on what they think their best action is. Okay, and so I've deliberately used the notation here coming from machine learning, because on Thursday we'll have a segment on scoring functions in machine learning. It'll be consistent to have the exact same notation. Okay, so in machine learning, you might observe some features of maybe an individual you want to make a decision for. Maybe you're giving them a loan, and you have, their education level, you have whether they've paid you have their credit scores, you have like other factors about them. That's your X, that's your signal. And that's going to help you update your belief about whether they're a responsible person or an irresponsible person, which is going to affect your payoff of if you just choose an action of giving them a loan or not, which is going to affect your payoff as a lender. That would be, for example, an example here. I'm going to use a much simpler example. Okay, so my state space Y is going to be 1 for rain and 0 for none. Okay, my feature space X is going to be 1 for clouds, 0 for none. My action space A is going to be 1 for umbrella and 0 for none. Okay, my joint distribution, I'm going to write as a matrix with rain, none, and clouds, and none. Here with 1/4, 1/4, 0, and 1/2. Okay, so if there are no clouds, if there are no clouds, it's not going to rain, right? And so these probabilities are going to sum to 1, of course, because the probability of in any one place has got to be a probability distribution, so it's going to sum to 1. So look, a quarter, a half sums to 1. Great, it's a probability distribution. If we see clouds, half the time, conditioned on clouds, half the time it rains, half the time it doesn't rain. Conditioned on no clouds, conditioned on no clouds, it never rains. Cool. And my utility function, I'll also write as a matrix. So U of A and Y. Okay, so here we're going to have, again, rain and none. And then we're going to take an action, umbrella, and none. Okay, and I'm just going to write payoffs that we're going to get in these states given the actions we take. Okay, so if it rains and we take an umbrella, our payoff is going to be 3/4. We're pretty happy we're not getting wet, but it's not great that it's raining. Yes, please.
Yeah, I'm just confused as to what the information setting is, like who knows what.
Yeah, so in the model, we have one decision maker. So there's only one person in the world. And they're going to see a signal and then make a decision.
Do they have access to pi?
They know pi beforehand, yes.
Okay.
So every day, this decision maker has been waking up, seeing clouds, noticing rain or not, and they've collected all this data, which shows them this. Okay, and now today, they're going to wake up, either see clouds or not, and want to make a decision. Okay, and they know what their payoffs are for various decisions, and so let me just write those down. Okay, so if we take an umbrella, and it doesn't rain, that's kind of annoying that we took an umbrella and it didn't rain. So I'm going to say 1/2 is our utility there. We're calling an umbrella around all day. Okay, if we don't take an umbrella and it rains, that is the worst for us, 0. We just got soaking wet. We're super unhappy. We couldn't attend the winter school because it was raining in Morocco. Rita promised us sunshine every day.
In the UK, you may not have clouds, but it will rain.
And of course, what we're hoping is we don't take an umbrella and it doesn't rain, and so we get this great payoff of 1. We don't have to haul an umbrella around. It's a sunny day. It's lovely, perfect, 72 degrees Fahrenheit. for people who know what Fahrenheit is. All right, so those are our payoffs. Cool, so at this point, I want to draw a picture of these payoffs as a function of, either it rains or it doesn't rain. Okay, and if we take an umbrella, sorry, let's do none. If we don't take an umbrella, right, and it doesn't rain, we get 1. Okay, so I'm going to do that. Let's do colors. Let's do colors. Okay, it doesn't rain, we get 1. And if we, again, we're not taking an umbrella, so no umbrella. And that was doesn't rain 1, okay, and no umbrella and rain is 0. So that's this point. Cool. Let's suppose you believe the probability of rain is some p. So you believe the probability of rain is p. What is your expected utility from not taking an umbrella? P times 1 plus 1 minus p times, sorry, p times 0 plus 1 minus p times 1. That's the line that connects these two. Right, this is expected utility from if the state y from p of none and y, which, as I said, 0 times p plus 1 times 1 minus p. Right? Everybody happy? Did it right? Oh, good. All right, now what happens if we take an umbrella? So if we take an umbrella and it doesn't rain, that's here, 1/2, that's our utility. And we take an umbrella and it does rain 3/4. Okay, now I need to somehow draw 3/4 on my plot. That's here, 3/4. Okay, and again, I can connect them with a line, right? Because if some probability p, right, that it rains, then if we decided to take an umbrella, we're going to get the expected y from p of u of umbrella and y, which is equal to 1/2, let's do this way, 3/4 times p plus 1/2 times 1 minus p. And you can simplify it and figure out what that line is. Everybody happy? Cool. All right. Let's suppose you don't have access to the signal. So what if you wake up and it's 7 a.m. in Morocco, and at 7 a.m. in Morocco, it's dark. Sunrise is at 8:30. And so you look outside, it's like, it's dark. I have no idea if they're clouds. So you don't have the signal. So we have to decide whether to take an umbrella without knowing whether they're clouds or not. So our prior belief is the expected expected value of y without a signal. And that is equal to what in this example? So if I don't have the signal, what's the probability that we're in this column? A quarter. What's the probability we're in this column? 3/4. So what's the probability of rain? 1/4. Okay, so I'll call that our prior, which I'll denote with P. And so P is here at 1/4. So, given our decision makers problem, what should we do if we woke up at 7 o'clock in Morocco and we didn't know if there were clouds? Right, we have a choice of getting this utility or this utility on average, right? And this one is higher, so we're gonna wanna make that decision. That is the optimal decision if we don't have the prior, if we don't have the signal. Cool. Okay, our optimal action is no umbrella. What's our posterior belief? That is the expected value of y given our signal x. Okay, and let's just do the two cases. What is our posterior if we see clouds? We're here, so we see clouds. So we update, we're only here. So we renormalize these by the total probability of 1/2. So multiply them by 2, right? And we get 1/2 and 1/2. And so the probability of rain is 1/2 if we see clouds. Okay, so I'm going to say Q of clouds is equal to 1/2. Okay, and if we see no clouds, then Q of no. Okay, so we're here. We wake up, we don't see clouds. Rita let us sleep in. We slept until 9 o'clock, civilized hour to get up in Morocco. We didn't see clouds. And so we're like, hooray, no rain today. Okay, we normalize by the total probability of 1/2. So 1/2 divided by 1/2 is 1. Probability of rain is 1. No rain is 1, so the probability of rain is 0. Everybody happy with that? Okay, so what's our optimal action? Good, so we can, sorry, for both these cases. What's our optimal action for if the probability of clouds is 1/2? So this is going to be Q of clouds at 1/2. We're going to take an umbrella. Good. And then what's our optimal action on no clouds? So here is Q of no clouds. So no umbrella, and we get this. So I'm just going to define some notation. If our posterior is Q, I'll let the optimal action be A super Q is the argmax over A in my action space of the expected value of if the state is drawn from Q of our utility given our action and given the state like that. Okay, that would be the optimal action to take. Again, so argmax, right? Max would say, what is the A that makes this as big as possible? Argmax say, what is the value of the utility that makes this as big as possible? And argmax says, what is the action, the maximizer, that makes it as big as possible? Okay, and some convenient notation, because I'm going to get tired of writing out this expectation. And so I'm going to define the following notation. We'll say U of A and Q is equal to the expectation of Y drawn from Q of U, A, and Y. Okay, in other words, if I want to fill in the expectation for the second argument, which I'm going to be doing a lot, then I can, instead of writing this out, I'll just write this. I'll put Q here, which means take expectations over this distribution. Cool. Okay, so I want to switch gears a little bit to talk about the value of information. So the idea is that information is valuable if it helps us improve our decisions. Okay, so if I look at this picture, if I didn't see the clouds, I'm going to get this payoff, which is three-quarters. Right, line from 1 to 0 over 1, so a quarter of the way in is three-quarters. Cool. If I do have access to the signal, what do I get? Well, with some probability, we get 0, right? Because we see no clouds and we don't take our umbrella. With some probability, we see clouds and we get this. And we mix with those with probability exactly to give us three-quarters, the prior, right? So if we get the signal, we get to mix between this and this with probability that gives us that. So I can draw mixing between these 2 points with this line, right? And the payoff I get from mixing between those two is this amount. Who can tell me what that is? Yes, please. 1 over 16th more. So you're saying that this distance is 1 over 1/6. Everyone believe them? I think that's right. Let's figure it out, though. Okay, 3/4 to 1/2. So this value is so this distance is going to be, it's going to be like 5/8, right? Everybody agree? It's like halfway between 1/2 and 3/4, so it's 5/8. Cool. And this value is 1, and so half of 5/8 is 5/16, right? So this is going to be 5/16. Okay, and 5/16 to 3/4 is going to be a distance of 1/16. Fantastic. Sorry, I was slower than you. What's that?
So Amar is assistant prof at the university, and he's also student at the program. He'll talk to you. So he's
Oh, cool. So we're talking about value of information. We did our example. Yeah, question.
Can you repeat how you pick the 2 points that you're like mixing between?
Yeah. So we asked what we would do with the information, right? And we said with clouds, our posterior belief given clouds, the probability of rain is 1/2 in that case. So we believe 1/2, and we're going to choose either between green or red, whichever is higher. So we choose red, which is higher. And that gives us this point if that's the utility conditioned on seeing clouds. If we see no clouds, the probability of rain is 0. So we're here with our belief, right? And we're like, which is higher, red or green? We're like, green, right? And so we get 1 in that case, okay? And then we're like, well, if we know we're going to see clouds, let's calculate our expected payoff before we see the clouds or not. Okay, so the probability we see clouds or not is, we look here, right? Clouds are with probably 1/2, and no clouds are probably 1/2, right? So we're 50-50 in between clouds and no clouds. Okay, and so we're going to either get this with probably 1/2 or this with probably 1/2. So we're halfway in between the 5/8 and 1, which is 5/16.
I see. So you're just trying to calculate your like total payoff from following this strategy.
Exactly.
Okay. So there's no like you're not mixing in your actions. You see the signal.
I am not mixing in my actions. I see the signal and I optimize the deterministic action that's optimal given the signal I saw. You're exactly right. Thanks for that question.
When you have the only decision maker, there is no reason to mix.
Yeah, but I was confused by the line.
Yeah.
Yeah, I get it.
Cool. Okay, so I'll call the value of the information the difference in the optimal payoff, the payoff we get from taking the optimal action conditioned on the information with or without the information. Okay, so it's exactly what I wrote here. And so let me just write that out. That is the expectation, whoops, expectation over x and y drawn from pi of the utility I get from the optimal action qx y minus the utility I get from the action p and y. Okay, so here, if I only know the prior p, right, I take the action qp, that's the what am I writing here? A. I take the action AP, the optimal action given the prior. Here, I'm going to get the posterior given the signal. So I'm going to take the optimal action for that, right? And it's the difference in these two payoffs in expectation. Okay, and in my example, the value of information, as we said, is 1/16. Cool. So if we had a so
What do you have inside?
this
Just to know.
ginger tea. So cool. So I mean, this definition of value of information is like a little bit, you know, it depends on a lot of things, right? It depends on the distribution of the information. Like so just knowing the umbrella or not, like you have to know what pi is to know how to update to how it's related to the state to know how the information is valuable. That's like one thing, right? But also it depends on the payoffs I get for having the information. So one thing we're going to be working towards is removing dependence on the payoffs. Okay, because we might like, and if we're going to be talking about machine learning on Thursday, we might like algorithms that make predictions to value information for any decision maker using those predictions, and not have to know about the payoffs of our individual decision maker who feels this way about getting wet or carrying umbrellas. Right? Someone else might feel differently about getting wet or carrying umbrellas. Or someone else might be looking at weather because, you know, when it's raining, people take Uber, Lyft, or InDrive more, right? And so they should try to get more drivers out by taking them more or something when it's raining, right? So like people might have different decision problems, and we would like probably a value of information not necessarily to depend on the individual decision maker so much. So we're going to be working towards that later. That's a little bit of motivation for what's coming next.
Does it also depend on prior?
Absolutely, yeah, it depends on the prior and depends on the decision problem. Now, I would say the prior is like somewhat fundamental. Like if you're doing machine learning, you're collecting data, the data is coming from, the distribution is coming from, and so you should have some beliefs about what the prior is, right? How to map your data, right? So the prior is going to be probably given in the machine learning problem. But what's not given is what everyone's going to do with your predictions after you make your predictions. And in fact, if we're doing algorithms, we really like having one algorithm that works well for any decision maker, right? So we're going to want to get rid of the dependence on the value of information on these payoffs. Yes, please.
We're going to consider only risk-averse, so expectation maximizers.
Yeah, so risk neutral. We're going to consider only risk neutral decision makers. Absolutely. I invite you in your PhD thesis to consider risk averse or risk loving decision makers. Yes, please.
I just have a question. Is it possible, which I think is not, to have negative value of information in this example?
No.
Okay, so we are quantifying the gain.
But it's not possible to have negative value for information because it's a difference between two things. It's a difference between the decision you would make with information and the decision you make without information. If you have information, you can always make this decision. Right? So this can never be lower than this. Great comment.
It's always positive.
Yeah, always non-negative.
So can I give a comment?
Yeah.
Zero-sum game and or in one decision problem, it's always positive. If you take non-zero sum, for people that want to do advanced game theory, the value of information can be negative. It's better not to have information than have it because it may change the behavior of the other people, and then you are screwed, and you prefer not to have this information. One is more.
I regret letting you make that comment. My value for you having that information is negative.
Also because this is risk neutral.
I'm not sure that depends on risk neutrality.
Because expected utility.
But I invite you to think about that on your own.
No.
It's just because expectation of the max is bigger than the max of the expectation.
That's a great point. We're going to use that in a proof later, so I'm going to call on you in the second segment when we need that. Absolutely. We're going to use that later.
So I feel like the value of information, if you project this problem in real setup, it depends on how much private information you have. Besides the decision-making environment, right? It also depends on how much private information you have.
Yeah, so when I write down a decision problem, I give you all of your information in the prior. So I'm talking about, again, there are no other people here. So the decision maker has this information. This is what they're seeing. So you're saying that, what if we're doing machine learning and we make a prediction for someone, but this person has access to other information that's not information our algorithm has access to, right? Yeah, then stuff is sort of not quite right here. You need to fix it. Okay, and so if you want to make predictions in machine learning for people who have extra information, extra data, you need to tell them how to interpret your predictions with the extra data they have. Otherwise, they don't know. Okay, so for example, and this is something that's very popular in machine learning, and mostly people look at it from a very applied, like HCI, human-computer interaction perspective, which is explainable AI. Like you want to make predictions, and you also want to give explanations for why that prediction is good. Why might you want to give additional information? Well, because if someone has their own information, there's a doctor looking at some x-rays, and the algorithm says this person probably has a broken bone. But the doctor has information maybe that the algorithm seeing the x-ray doesn't have. Okay? And so you might want to provide an explanation, additional covariates that the doctor can use to combine their own information with the prediction you're giving. Okay, and so in that context, if this is a machine learning, we have the y we're trying to predict, right? Broken bone or not. We have x, which is all the details of the x-ray that the algorithm gets to see, right? And we're going to make a prediction probability that it's broken or not. We might also say, look at this part of the x-ray where we see the thing happening that makes it broken. Like, so we'll reveal part of the x to the doctor so they can combine that with their own information to make an even better decision than they would have just ignoring any information they have and following the algorithm. Okay? And one of the reasons why I'm sort of excited about people knowing this framework is, as I said, the people thinking about explainable AI are mostly thinking about HCI studies and this not, and they don't really understand decision problems and decision theory and the stuff I'm just describing here in math. Okay, and I think this mathematical perspective can help illuminate what people are doing with explainable AI. So exactly tackling the suggestion that you just made. But let's try to keep it simple today, and let's not do that. But I invite you to write your PhD thesis on that, or
so
if you're...
There's a question. Do you mean that people that do many people, most of the community doing explainable AI, not necessarily using these models behind?
That's correct. They have no idea.
Okay.
They're not mathematicians. They run experiments, they collect data, and they see what algorithms work better. I have a couple very new papers with an HCI colleague of mine trying to understand how to use decision theory to give foundations for things like explainable AI. But, and actually, my perspective thinking about scoring rules has what's brought me to this point where I'm like, oh, this mathematics is going to be really good for understanding how to make use of AI predictions and how to make AI predictions more useful and treating things like you just said, because you say, oh, what would be the model of that? Oh, there's some extra information. And then you don't want to just make a prediction. You want to tell people how to combine your prediction with their extra information, right? And that's exactly explainable AI. And so you come at like what people are doing in practice by asking these questions. Cool. All right, proper scoring rules. Okay, so we're eliciting probabilistic beliefs. Okay, so a belief, it's exactly what we're talking about here. I'm going to notate it by P in this notation, delta, and then a space, which means these are distributions over the state space. Okay, so let me give some examples. So if the state space is y is 0 or 1, then p is just equal to the probability when y is drawn from the distribution p that y is equal to 1. Okay, so we'll say p is in the simplex. If we have two possible outcomes, 0 and 1, well, I'm just going to tell you the probability of 1 because the probability of 0 is 1 minus the probability of 1, and so I tell you everything with the probability of 1. So that's what I write down as my p. Okay, but I might have some multi-dimensional y, and so I'm going to generally write that as 1, 2, up to k. Okay, and then it's going to be most convenient to say that p of little y is equal to the probability when we draw y from p that y, what am I doing here?
Small k, right?
We'll say p of j, the probability that y is equal to j. Okay, so we can view this belief p as now a vector with entries p1 up to pk, telling you the probability that each of these outcomes, y going from 1 up to k, arises. And this is a little bit redundant, right? Because if I tell you the probabilities of 2 to k, then you can compute 1 because it has to sum to 1. So it's all the remaining probability. It'll be a little bit redundant, but we're not going to worry about it. Everybody happy? And I'm just going to use the notation p either just like this for the distribution. And if it's a binary, then p is just a number, the probability of 1. And if it's not binary, p is going to be a vector, which will be the probability of every outcome arising. Okay. So a scoring rule S takes a distribution over states and a state and gives you a real valued payoff. Okay, so S is going to map a reported belief. Okay, my forecaster is going to say, I think the probability of rain is 20%. And a realized state, did it rain or not? To a payoff they get. Okay. This board has something written on the back. Who did that?
Ah, you write something? Yeah. Yesterday. Did you sleep here yesterday? Do you want to change it?
I would have liked to, but something is written on the back. Okay. So a scoring rule, as you see I wrote it there, is just a decision problem, right? So compare it to this, right? U of action and state, where the action space, the things I'm allowed to do, are distributions. They're beliefs over the state space. Okay, so one of the reasons why I like presenting scoring rules from decision theory is it's a special case. Okay, so in a scoring rule, you're going to take an action. That action is going to be a probabilistic forecast. You're going to say what you think the outcome is going to be. Okay, so a scoring rule is proper if truthfully reporting your belief is subjectively optimal. And I want to note that I deliberately added the word subjectively here to remind you that when we talk about properness, we're always saying, I've got a forecaster who's got a belief over the state Y. Okay, so when I evaluate their utility and whether they should report their belief, I'm going to evaluate their utility and expectation over the belief that they report they have. Okay, and so properness says, given the belief that you are saying you have, the belief that you have, the optimal belief to report is actually that belief. Okay, so we're pretty soon going to be thinking about optimizing scoring rules. So we might have in mind someone else who's trying to optimize the scoring rule for this forecaster. And then someone else might have their own prior. Their own prior does not matter for properness. What matters is the belief of the forecaster. And so we're checking the forecaster's subjective belief and whether reporting their belief truthfully is their best strategy given their belief. Okay, so what does this mean? This means P is in the arg max over R of the expectation of Y drawn from P of the score on R and Y. Okay, so imagine we have a subjective belief, we're the forecaster, we have a belief P over the state. Okay, so I'm going to try to then optimize my report in the scoring rule. So to maximize my expected utility, I think the state Y is drawn from P. I'm going to figure out what report R maximizes my score when Y is indeed drawn from P. Okay? And if it's proper, that means that the report that maximizes my score is indeed the true belief I have. Yes, please.
Can I am a student also. Shall it be, so is there a distinction between the scoring rule when it is unique argmax and the one where there are many argmax? Or no?
Yeah, so we will call it strictly proper if it's unique. Yes, please.
So my question is, how do you, let's say, elicit the scoring rule in this case?
That's, I think you might have not used the words you wanted to use. So typically, we assume that a decision problem is given. And if we are trying to elicit a belief from an agent, we are going to perhaps design the scoring rule. Okay, so can you ask your question again? Because I think you might have used the wrong words and I didn't understand the question.
No, I mean, where does the scoring rule come from? How do you?
Yeah, so you know, maybe I'm doing an HCI study. I've got a lot of behavioral participants in my lab, and I show them some stimuli, and I say, what do you believe is the outcome of some variable given the stimuli you saw? And I'm going to reward you with the following payoffs. I'm going to give you more money, you know, in some cases than other cases based on what you report. And so I'll come up with a scoring rule myself. When I give exams to my students, I ask them what their beliefs are about some true-false questions. Is it true or false, right? And then I take their answers and I tie them up into grades and I give them some points on the exam. I came up with a scoring rule, right? I come up with the way to take their reports and come up with a grade on the exam. Okay, so usually there's a principal involved who wants to come up with what the scoring rule is. Yes, please.
For these scoring rules, are we thinking about the decision maker getting signals or no signals, just the prior?
We will be thinking about that, but in a little bit. So just hang on a second. Because if you remember my previous picture, right? We cared about drawing the payoffs of what would happen for any belief here, right? And then we looked at it for the prior P and for the posteriors Q no clouds and Q clouds, right? So we plugged in all kinds of beliefs into this payoff function when we had information. And so to begin with, we're going to want to start defining scoring rules given just some belief you have. And then maybe there's a distribution of our beliefs given some information you have. We'll see that later. Man, I wish someone hadn't written in permanent marker on the back of that board. On day one. What were we talking about? Oh, yeah. All right. Okay, so again, my perspective on scoring rules comes really from mechanism design. So mechanism design, maybe we're talking about auctions. We want people to bid how much items are worth. We're going to sell it to them. We care about truthfully saying how much your values for these items are worth. That's like properness. It's called incentive compatibility in mechanism design. And so really my philosophy is like, oh, let's understand proper scoring rules from all the stuff we know in the huge literature on mechanism design. And if you know one thing in mechanism design, you should know the revelation principle. And that says that if I have a mechanism that I like that's not truthful, where you're going to strategize, I can always come up with another mechanism where I get the same outcome where you just truthfully report. Okay, so if I have a decision problem where you need to pick some funny action doing some crazy strategy given your beliefs, I can always come up with a proper scoring rule that has the exact same thing happen, and you just report your belief truthfully. Okay? Yes, please.
But the scoring rule would depend on.
Absolutely.
Yeah, how strategic.
The scoring rule, sorry, in this case, the scoring rule doesn't depend on anything because I only have one agent.
Yes, but if we had, yeah. Okay.
We only have one agent for scoring rules. So actually, the revelation principle for scoring rules is way easier than the revelation principle for mechanism design because I only have one forecaster. Cool.
But we may want to reveal information from different forecasters. Another.
In the PhD theses you guys are all going to write, you can have multiple forecasters, and I am looking forward to reading those papers. So the proper scoring rule for decision problem U is just this. S given report, which is my belief, and the state space Y. I'm going to define it just to be the payoff that I would get if I take the optimal action for that belief in the decision problem U when the state is Y. Okay, so it basically it's like delegation. You're like, oh, you have a decision problem U? Tell me your belief. I will just take the optimal action for you given your belief and play that in your decision problem. Yes, please.
I'm sorry to bother you on this, but why do we go through the pain of working with scoring rules when we have one agent? Like, why is it useful as a notion?
So it's going to be, so in other words, I feel like you're saying, why is properness useful?
Yes.
Versus looking
one
at
agent.
improper decision problems where I just ask for actions.
Like, I can see why this is useful if I have many players.
Yeah, let's ask me that question at the end of the 3 hours, like in the lunch break or something.
Yeah.
Because we're going to do a lot of stuff. And the first thing we're going to do is characterize properness, just like we do in mechanism design. And that's going to simplify our life a ton. Okay, so we're going to see why properness is useful. For my HCI studies, I probably wanted someone actually to report the distribution they believe. And so there I really want a proper rule, right?
That I understand. If I have many players, I want all of them to be simultaneous.
No, but see, these HCI problems, they're just doing individual studies for each person, and there's no, like the payoff for one player doesn't depend on the actions of other players. Yeah, I mean, I tell them, like, you know, depending on how close you are to being right, I do something, and rightness doesn't depend on other players, so it's not a game. I saw another hand up somewhere. Yes, please.
So, like, I think I'm a little bit confused. Like, who's the decision maker and who's from who are we eliciting the belief that are two different people?
No, that's the same person.
So, there has to be one person setting the scoring rule and one person responding to the scoring rule, right? Or
That's correct. So the principal might be like, oh, I want to collect a bunch of beliefs from people about, you know, something.
So the principal has a decision problem and some agents that he wants to.
This is a little bit confusing right now. All I'm saying is that if I want to understand, all I'm saying is that if I want to study decision theory about how people make decisions, actually there's a sense in which understanding scoring rules is enough. We're going to come back to it later where this connection is very important and who's whom is going to make more sense. But for now, it's just, oh, look, isn't this neat that for any decision problem, I can come up with an analogous scoring rule where basically the same thing is happening. Okay? And in my scoring rule, the decision maker is the forecast. In my decision problem, the decision maker is the decision maker. Right? And so don't think of them as different people right now. Yeah, but this connection is going to be very useful later.
I think here you want to present them as mathematical objects. If you maximize this, then you will have the definition satisfied somehow. For the moment.
Cool. So if I was going to apply the revelation principle to this decision problem, what am I saying? Yes, please.
Just a quick clarification question. Why are we, let's say, conditioning the scoring rule on the state? So it means that if you compute the argmax, then you have a different argmax.
No. So let me. No, that's not quite right. So let me go back to this. It's a great question, and it's not quite right. Let me just clear up this misconception. So in this argmax, I'm choosing R, which is this parameter. You have a belief about whether it's going to rain or not. I'm going to score you to evaluate how good your belief R is based on what actually happened, the state that realizes. Right? So I asked you to predict the weather. Right? It'd be nonsense if I asked you to predict the weather and evaluated you without ever looking at what the weather was. So I have to look at the state to evaluate how good your prediction is. You see what I'm saying? I'm in the business right now of evaluating, is your prediction good? Okay, so you say probability of rain is 25%. We see it didn't rain. Is your prediction good? How much should I reward you for saying 25%? Right? Probably I should reward you more if it didn't rain and you said 10%. Right? Yes, please.
Suppose your belief is depend on a hard evidence, and suppose
This is too fancy. Come, let's talk about that in the break. Yeah. Yeah. Cool. So I was just saying, look, there's a revelation principle where I can define a scoring rule as the utility you would get from taking the optimal action. Okay, so what does that mean for this decision problem? Yeah, so the point is I need to compute this point, right? The point where you switch your action from taking, what is this, the no umbrella versus taking the umbrella, right? And so this value actually turns out to be 2/5. You could calculate it. I did. Took me a while. Not as fast as our colleague here. 2/5. Okay? And so the point is you're going to make a report. If your report is above 2/5, I'm going to pay you off according to this line. If your value is below 2/5, your report is below 2/5, I'll pay you off according to this line. And that's going to have the exact same result as if I let you play in this decision problem, right? Because in the decision problem, you would take the better of these two lines given your belief, right? Which would be the exact same payoff. Okay, so we can write that out. Okay, it was y over 4 plus 1/2, right? Because it went up a quarter and it started at 1/2. So it's y over a quarter plus 1/2 if r is greater than or equal to 2. Oops. Right, it's 1 minus y if r was less than 2/5, right? You guys agree that was the same function I drew before? Cool. Yeah, we're good. We're doing great. Oh, I could get one more board if I go over here. Cool. You guys can all see that back there? Yeah? Am I already big enough? Cool. Actually, I'm not going to use this board before the break, so we'll just write here. Okay, I want to talk about eliciting the mean. So in many, many problems we care about, we want forecasters, like imagine instead of like rain or not, we want to know what the temperature was. Okay, and so we want our forecaster to say, you know, we believe the high temperature today is going to be, I don't know, 22 degrees. The low temperature is going to be 22 degrees because the weather in Rabat is perfect. And that's going to be the expected value of the high temperature given whatever data they have. So you want to elicit the mean of a distribution. That's not going to be the example I'm going to use. I'm going to use an example of peer grading. Okay, so what's peer grading? So I've got too many students in my class, and I don't like grading all their homeworks. So I'm going to have them grade each other's homeworks, and then use those to calculate the grades. That's peer grading. The problem is that if you want students to do anything well, you have to grade what they do. So you have to grade the grading. If I ask students to do peer grading, I better grade the grading. And so I wanted to save myself some work by not having to grade all of their homeworks. But I asked them to do peer grading. But then I created all the peer reviews, and now I have to grade the peer reviews. Okay, so that's so how to grade the peer reviews. So here's how to think of it. A peer is going to look at the submission, and it's going to report a grade of R between 0 and 1. Okay? And I'm going to look at the submission. And report a grade of Y between 0 and 1. And the question is how should I grade the peer review? And if I've graded the submission, I'm pretty sure that my grade is correct. And so I want to grade, I'm going to call my grade the truth, the state. I want to grade this peer by how close they are, how well they are predicting what I would give this submission. I want them to become little copies of me doing all the grading exactly as I would do it. Okay? Okay, and the approach we're going to try is use a scoring rule for belief R against truth Y. Okay, and cool. So now we're trying to come up with our own scoring rule to use, right? So I'm the instructor of the class. I'm going to figure out what scoring rule I should use. And I've looked at statistics literature, and I know that a lot of people use the quadratic scoring rule. So let's just write it down. Okay, and in machine learning, the quadratic scoring rule is just squared loss. So it's one of the most common loss functions used in machine learning. It's also one of the most common scoring rules used. And so the quadratic scoring rule is S of R and Y. So I want to evaluate the peers report against my review. Okay, I'm going to give grades always between 0 and 1. So I'm going to start them off with full credit. And I'm going to subtract out the squared error. Minus R minus Y squared. Okay, that is the quadratic scoring rule. Okay, so for example, if R is equal to 3/4 and Y is equal to 1/4, then S of R Y is equal to 1 minus 3/4 minus 1/4 squared. This is 1/2 squared. So that's going to be equal to 3/4. Everybody very happy with this?
One student is reporting over someone else.
That's correct.
Only one person.
I'm just going to look at one person because, again, I have all the points. Right? I can get points out however I want. I have all of them. The students want them. I have them. I don't have to have the students compete with each other. So when I grade one student's submission, I don't even look at any other students, what they're doing. Yeah. I just want to incentivize one student to give a good review. If I can do that, then I can just copy the same thing for everybody else, and they all give me good reviews.
For that to make sense, a good review should be independent of the behavior of this, like the behavior of the student. The prior.
That's right. That's because the good review is equal to y, which is what I put in.
Okay.
I did the grade of y. Here's the problem. How does peer reviewing work? So there's a state y they're trying to predict. That's my grade. They have a signal, which is look at the submission. Right? X is just the submission they're grading. Right? They have an action, which is reporting a belief. Right? And then there's a joint distribution over the signal, like what they see the others working and what they think that I'm going to grade, how I'm going to grade things, right? They like, oh, there's a distribution over reading the submission. Is Jason going to give it a high score or a low score or what? Right? And then they get some payoff from a scoring rule of reporting their R, right? This looks just like this. Here's what I'm worried about. It takes some work to look at the submission and understand if it's a good submission or not, right? You have to it could be like in algorithms homework that I teach algorithms. My algorithms homework sometimes are like 5, 10 pages long when they turn them in. Yeah, reading that's just gonna take you like some time. Okay, so there's something I didn't model here, which is getting the signal in the first place takes some effort. There's maybe a cost for getting the signal, right? And that's why, coming back over here, this value of information could be important, right? Because if the value of information is less than the cost of getting the information, you could just go with your prior. So let's try to evaluate what that looks like. So just as an example, back of the envelope, put, what could happen here. Is putting in effort to learn your signal worth it? So let's just put some numbers here. So we have a lazy peer, just going to report the prior. What do you think the prior is in my algorithms class? I think the average grade is 80%, right? Typical average grade. So that's P equal to 0.8. Okay, or you could do hard work. Okay, and you can put in effort, and then you can report posterior. Okay, and but what if you think, come on, what if you think that I always give grades between 60 and 100? Or most of the time. I almost always give grades between 60 and 100. So what if you think that y is going to be between 0.6 and 1. Okay, so if y is between 0.6 and 1, then the lazy peer, right, the worst it could be by saying 0.8 is being off by 0.2, right? So the lazy peer is at least 1 minus 0.2 squared. That's 0.04, right? That's at least 0.96, 96%. Not even looking at the submission, you get a 96%. Okay, or you can spend an hour of your life reading 10 pages of this algorithms homework, right? And the most you could get, you know, the hard work well, that's going to be less than or equal to 1, of course. That's the best you could do, right? So your value of information is at most 0.04. You're probably not going to do any work. You're probably going to say 0.8 every time on this homework and never, ever look at them. Incentive for hard work. Incentive for hard work is less than 0.04. Okay, so the quadratic scoring rule kind of sucked. And so that's going to motivate this question we're going to be spending most of our time after the break on, which is, are there better scoring rules? And our approach is going to be the following. We're going to first characterize proper scoring rules, characterize proper scoring rules, and then we're going to optimize over proper bounded scoring rules. Okay, so one point to make here is that notice the quadratic scoring rule is always between 0 and 1. So are my grades. I don't want to give someone a grade less than 0. I don't want to give someone a grade more than 1, full credit. Right, so grades are always going to be 0, 1. So I need my scoring rule to be bounded, right? I do want it to be proper. Someone was asking before, why do we care about properness? Like, I'm getting peer reviews. I'm going to use them to grade. I want numbers that are best predicting what what they think that the instructor is going to grade it as. Yes, please.
Do you use the logistic or hyperbolic tangent for that?
Do I use the logistic?
Hyperbolic tangent instead of quadratic?
Have I tried that? So what we're going to do after the break is optimize over all scoring rules and find the best one. And it won't be that one. Cool, let's have a break. Okay, welcome back, everybody, to the exciting after the break session. Cool. Our plan is to talk more about eliciting the mean, characterizing proper scoring rules, optimizing over scoring rules. We decided the incentive for effort of the quadratic was very low. We want to find a scoring rule where my peer reviewers are going to be more incentivized to actually look at the submissions and give them a good review. And then we'll talk about elicitable properties, hopefully. The first thing I want to do is say, just come back to proper scoring rules. So when we define proper scoring rules, we're talking about eliciting the full distributional belief. When we're eliciting the mean, the forecaster shows up with a full belief, but we only want them to report the mean. So we want it to be the case, if we were looking at this, that we want the expectation of P to be in the argmax of our reports of their belief given the full belief P of the scoring rule. Okay, so the only difference between reporting the mean is I write the mean of the belief here to be in the argmax. Okay, so just to make sure that that little change is clear for everybody. Cool. So I skipped something before the break because we didn't quite have time, so I want to go back to it. And that is the following theorem. So the quadratic scoring rule is this. And so what I would like to show is that the quadratic scoring rule is proper. In other words, reporting R is equal to, expectation of P is optimal for the quadratic scoring rule. So the proof I'm going to give you is not probably the normal proof, but it's the proof that has a lot of geometry, that gives a lot of intuition for what proper scoring rules look like. So I'm going to give you sort of the geometric argument for why the quadratic scoring rule is proper. Okay, so I'm going to let g of r be this function. 1 minus r squared. Okay, that function looks like this. One minus r plus r squared. Okay, that function looks like this. We can try the endpoints, plug in 0, we get 1 minus 0 minus plus 0 is 1. Good, we plug in 1, we get 1 minus 1 plus 1 is 1. Good. So we can do some algebra to rewrite the scoring rule in the following way. I'm not going to do this algebra, but you guys could all do this algebra. I'm going to rewrite the scoring rule in terms of G. Okay, so S of R and Y is equal to G of R plus the derivative of G at R times y minus r plus a function I'll call kappa of y. Okay, so I'm going to rewrite this function in terms of g this way. Okay, it's the function evaluated g plus basically something that looks like so this thing is going to look like evaluate the tangent, basically. So what this is the tangent at R plus some other thing, and that other thing only depends on the state. Okay, so I'm writing the score in terms of the tangents to this function g and something that only depends on the state. Okay, we care about the agent's incentives. And so we don't care about kappa, right? The agent's going to get kappa of y regardless of what they report. So we don't care about kappa of y. So if we're thinking about incentives, it suffices to only think about the tangent of this function u, of this function g. Okay, so here's the picture. We're going to make a report R, and we have this function g, right? And so we're going to look at g at R. That's this value, right? And then we're going to add to it the derivative g of R times how far away y is from R, right? So if y is, here, right? We're taking basically this tangent and we're getting this value. You guys with me here? Okay, this is the tangent at R, and we evaluate the tangent at R at y. So let me just write that down. I'll call that h r of y is equal to g of r plus dg of r times y minus r. Okay, so this function here is h of r of y. Cool. So if you were evaluating, so again, my incentives are governed by this. If I report R, I'm basically saying whatever y that shows up, evaluate it on this tangent. Right? I'm getting my payoff just from this tangent of wherever y shows up. Y shows up here, I get this. Y shows up here, I get this. Y shows up here. I'm just picking out that tangent to be evaluated on. That tangent is a linear function. We evaluate a random variable on a linear function. It's the same as evaluating its expectation by linearity of expectation, right? So all we need to know our payoff of this function is the expectation of our belief. Okay, so if we have some expectation of the distribution, right? The payoff we expect to get is exact, and we report R, but this is our expectation. We expect to get this payoff, right? And so if I believe the mean is R, sorry, if I believe the mean is E of P, and I report R, I get this. Okay? This function is a convex function, which means every point on the function is above every supporting hyperplane. Okay? In particular, if I reported the truth, or if I reported E of P, I would get evaluated on this hyperplane, and I would get this amount. Right? This is going to be G of the expectation of P, the expectation of my belief. Okay? And since every point on the function is above every single supporting hyperplane everywhere, we know that this distance is always a positive distance where this is worse than this. Okay, so G of E of P is greater than or equal to HR of E of P for all R. Okay, so truthful reporting of your belief is the optimal strategy because that's when you basically get this. Everybody happy? Nice little proof by picture. Okay, so the reason why I did this proof by picture is because, what should I erase? And where did I put the eraser? Is because every single proper scoring rule is going to look like we have a convex function G, and we evaluate the state on a supporting hyperplane of that convex function. Okay, so basically the geometry, and actually the proof. Okay, so the if direction we just saw. Okay, because the only assumption we used here in this proof was that G was convex, right? G was convex, which implied every supporting hyperplane is below G, which is the only thing I needed to know about G to write this proof down. Okay, so the other direction is a little bit more complicated, so I'm not going to prove it. And again, the reason why I like giving this proof that the quadratic is a proper scoring rule for the mean is because it allows me to exactly see the characterization of proper scoring rules. How you guys doing? Thank you so much. I was like, you guys should ask a question. Everyone's tired from having too much coffee.
G has to be convex.
That's correct. Exists. You're absolutely right, and I omitted that in error. That's fundamental. Yes, please.
Does G also have to be differentiable, or can we like work with subgradients?
You can use pseudo-gradients instead, yeah. Yes, please.
So the reason why this characterization is similar for the mean is because of linearity of expectation.
That's correct.
For moments, it would be like a different.
That's a nice comment. I'll tell you how to understand scoring rules for moments because moments are just means of the exponentiation of a variable. So I can use the characterization for means to get the moments. Great comment. Anything else? I think I was erasing this. Cool, so I want to talk about optimizing scoring rules. The example I'd love you to have in your mind is the peer grading example we had, no, here, right? Yeah, peer grading. Okay, so I have a peer report in 0, 1, I have an instructor report 0, whatever. You know, we want the students to want to put in effort. Okay, so how can I maximize the incentive for gathering information over proper bounded scoring rules? So the first thing I want to do is write that as a mathematical program. Am I writing big enough in the back of the room? Yeah. Yeah, good, thank you. Okay, so we're going to have max of our scoring rules S of the expected Q and Y are drawn from the prior distribution. And so now, basically, when they get their signal X, they're going to update and get a posterior Q. So I'm just going to write that in my notation rather than bothering with X. Because what they're going to do is get a posterior, so I'm just going to write posterior and Y as my information structure. So they're going to have a distribution where they get the, and when I see Q, the expectation of Y conditioned on Q is Q. Okay, so maybe I should write that. E of Y given Q, Q is equal to Q. Okay, of the difference in score with the posterior and with the prior. Okay, so that is going to be score, putting in, oh, it's going to be expected, no. Yeah, I'll say expected Q and the state state Y minus the score and the expectation of the prior and Y. Cool, so just to be clear, Y is our random variable, which is now like a real number between 0 and 1, right? Q is a posterior belief, so Q is going to be a distribution over 0, 1. Okay, and we care about our score when we report the expectation of Q, so the mean of the distribution Q. And we want that to be as big as possible compared to reporting the expectation of the prior, P. Okay, again, so I should have written this. Pi is given, and P is the prior of Y. Okay, subject to, S is proper, and S is bounded. Okay, and here I'm saying I don't want to give people grades less than 0 or more than 100%. Okay, so that's going to basically mean for all reports and states, S of R and Y is in 0, 1.
Sorry, can you justify again why you optimize this problem? So I am the expectation. Here you report Q.
So here I'm reporting the expectation of Q.
Yes.
I want to report the mean given my belief Q. Okay, that's if I have the posterior. And I want the score I get from the posterior to be maximally different from the score I get with the prior. So this is actually not a random variable, so I could have, oh, this is a random variable with y. So I do need that.
But who wants this?
Huh?
Who wants this?
So again, I'm worried about my lazy, I'm the instructor. I'm the instructor coming up with a way to grade my peer reviews. And I'm worried about the following. If the students can just put in the class average and get a really good grade, right, then why are they going to spend a lot of time reading the submission to get a posterior to put in a better, more accurate grade?
So this is the maximum you can do with respect to some cost that you don't know, in some sense.
So I'm not writing the cost. I'm just trying to make these as big as possible.
Yeah, but this is the
Right?
maximum we can do.
So if this is as big as possible, then students with the highest costs will agree to do the work.
You maximize the number of people that will do the work. Because
Exactly.
You are looking at the maximum salary
Yeah.
or bonus you will.
Yeah, so what Rita's getting at is I'm not modeling cost here. I'm just maximizing effort. Yes, please.
You're saying this is effort because we're assuming people are neutral. So like this different. What I've been trying to understand is why we say 0.04 is small.
Because if I told you that you would have to put in effort, and then I would change your grade by 4%. So you get a 96 without effort, and you get 100, most 100 with effort. And your other option is like going to watch the football match with your friends. You're going to go watch the football match with your friends. You're right that I need to have exchange units for points in my class versus time spent looking at the submission, right? In order to figure out exactly what's happening. I'm just going to ignore that. I just want to make the incentive for doing the submission as big as possible. And just ignore everything with the units of the effort and cost and whatever.
So it does not depend on the cost, but it will depend on the prior and on the P.
So again, P comes from this.
Pi and P. No, the S, the maximum S will depend on pi and P.
The maximum S depends on pi, the prior.
And P also.
Well, P comes from pi.
Ah, yeah. Yes.
P is just the marginal distribution of the state,
Okay, good.
y.
So only pi.
Cool. So I want to rewrite this again.
Question of modeling. Just to modeling. So pi is, so in your problem you have in mind, pi is somehow given. For example, when you grade students, you have an idea.
Yes. So again, when I try to look at scoring rules with the perspective of mechanism design, I'm going to assume the principal who's designing the rules of the system knows what the distribution is. Okay, so I know what grades the students are likely to get, the distribution of the posteriors people will get if they put in effort or if they don't put in effort. I also know my own distribution of grades when I grade the homework. So I'm assuming I know that. Okay. So I want to rewrite this using our characterization of proper scoring rules. Okay, and the first thing to note is that this is basically evaluating the score at the true belief, right? If the true belief is correct, because it's a proper scoring rule. And this is evaluating it as if the true belief was the prior, right? And so since we're using this difference of scoring rules, we can simplify it a lot. First off, score minus score means this kappa term is going to cancel from both the terms in the score. So we're not going to need that. Okay? And this is going to have expectation 0 if we report the truth. Right? So we're assuming the person here is reporting the truth because it's a proper scoring rule. So this is always going to be the truthful report. So this term is also 0. So if we rewrite with G, we're going to get max over G, the expectation of, I think I can simplify that too. What is it? Yeah, I'm just going to say Q. Max over G, expectation over Q of G of E of Q minus G of E of P. Subject 2, G is convex. And I need to put in the constraint for bounded. So I'm just going to tell you and not prove it. I think it's going to be an exercise in the afternoon for you guys to prove this, that the bounded constraint you can write in terms of G to say the endpoints of tangents differ by at most 1. So what I'm saying is, here we have a tangent, right? This is one endpoint, this is the other endpoint. What I'm saying is this distance is at most 1. Okay? And if I have a convex function, the biggest distance is, of course, the extreme tangents. So this one and this one. And so I'm saying the extreme tangents have distance at most 1. Okay, and if you think about it, look, you know, if you report this but we're wrong and the answer is here, right, you have to have 1 unit of difference in score. Right, and if you report this and the outcome was here, you have 1 unit of difference of score. Okay, so that keeps the boundedness constraint. Okay, so that'll be an exercise for you guys to do to the end points of the tangent are at most 1. All right, so that's my mathematical program. So I want to optimize over convex functions G. This thing, such a blah. Everybody happy? I don't think I need decision problems anymore. Cool. Yeah, notes. As I said, kappa counts from the objective, and algebra to simplify the boundedness constraint. What do I want to say again? I just want to, I think I didn't say this before, but I really, because when I look at this objective, kappa cancels. I don't care about kappa. And when you tell the truth, you actually get evaluated on G. I think of G as like the utility function that the player gets for telling the truth. Okay, so what this is saying is you're giving the truth-telling player a convex utility function. Okay, and you're saying the scores you get come from the supporting hyperplanes of that convex utility function. That's the characterization of proper scoring rules. Yes, please.
Make sure I understand the randomness here. In your simplification, when you use the characterization, now the second term is not random.
And the second term is not random at all.
Okay. So it's like okay.
The second term wasn't really random before because I could have put in P there, which was a constant, and just say S of E of P and P.
It was random in Y, but we got rid of Y.
You can get rid of Y, yeah. Okay, so theorem. Okay, so the theorem is that the optimal scoring rule is V-shaped at the prior mean expectation of P. Okay, so just to draw a little picture, 0, 1, it's going to look like this, where this is just the expectation of P. What does that mean? Well, we saw a V-shaped scoring rule already, which came from our decision where we don't take an umbrella over here, and there's the 2/5, and we take an umbrella here, right? This wasn't an optimal scoring rule for this decision. Notice because the prior, I think, was 1/4, and the kink of the V is not at 1/4. So this would not be an optimal scoring rule for this information structure, okay, for this prior. Okay, the optimal score is V-shaped, and the kink of the V, the place where you want to switch your actions, is exactly at the prior mean. In other words, what I'm going to ask the students in my class is, do you believe this submission is above the mean or below the mean? Okay, and if they say above the mean, I'm going to evaluate them on an increasing function. The higher my grade is, the more score they get, the higher score they get. If they say it's below the mean, I'm going to evaluate them on a decreasing function. The lower my score is, the higher a grade they get. Okay? Right? Because scoring rules, your report just picks out which tangent you want to be evaluated on. There's a convex function. There's a convex function G. And we would make a report that picks out which tangent we get evaluated on. In a V-shaped rule, there are only two tangents. The tangent above the mean and the tangent below the mean. So any report up here gives you the same tangent. So it's not going to be strictly proper, right? You're not going to be wanting to report your true belief exactly. It's going to be only just proper. Okay? Cool. Let's prove it. So we're going to...
There are many U-shaped functions, so I think the maximal tangent to maximize.
Let's see the proof. You said there are many V-shaped functions? Yes, please.
Like here, it seems like if you're asking for the report of the expectation, but you're only using it to create this like binary signal of like above the mean, below the mean. Like, doesn't it make sense that like you could like glance at the paper for 5 minutes and assess that versus like giving an actual grade?
That's a good question. So you're saying my model of effort for peer review might not be rich enough.
Okay, but like it is
Because in your model that you just made up, there's a glance at the paper, low effort, determine if it's above or below the mean. And there's a more effort, which is figure out exactly what the score is. Great question. I don't know the answer to that question.
so here all we have is like there's two options. You either put in effort
Yeah.
or you have the prior.
Yeah.
At the prior you're completely random.
And I would think of my example of peer grading as like just an example of a situation where there's either you have access to an information structure or you don't have access to an information structure. And maybe it's costly to get the information structure. We spent a lot of time thinking about how to generalize this to having multiple levels of effort. And it gets quite complicated quite fast. Great question for additional exploration. If you find a good application where there's a good model, you can maybe write a great paper on this topic. Cool, let's do this proof. Me. Yeah, it's our paper.
So which year?
It's 22, EC 22.
So this means that all these questions has meaning for
Yeah.
future research.
Yeah, it's very new stuff. As I said, like it's mind-boggling to me that, you know, the literature and statistics has studied scoring rules for, you know, over half a century. So this characterization, the first characterizations of scoring rules that look like this supporting hyperplane is from McCarthy in '56. Okay, so like basically 70 years ago, we knew what proper scoring rules look like. And like, there's no literature on optimization until we started asking these questions and wrote a paper 2 years ago. It's like unbelievable. No one cared which scoring rules were good. Yeah, okay, let's prove this. So every scoring rule by our characterization is given by a bounded convex function g. So let's start with that convex function g of a scoring rule you think is good. What I'm going to do is make it better by making it v-shaped at the prior mean. Okay, so this, sure, let's erase that. So I want to draw a picture. Okay, so I have some g 0, 1. That's going to be my bounded scoring rule. My scoring rule will be defined from this. Okay, so I want to consider replacing with the v-shape at the mean of the prior. Okay, so if I have some prior e of p here, I'm going to replace g with this. Okay. First thing I want to observe is that when I go from black to blue, I weakly improve the objective. What's the objective? Where to go? Other side of the board I'm now drawing on? That's terrible. Okay. No, it's not. Oh my goodness. Amazing. I didn't have that signal before, so I was operating with my prior. Okay, let's draw this picture again. Okay, so my objective is the expected difference over Q of the expectation of E of Q versus G of E of P. Right? So E of Q is going to be a random variable over here that I'm evaluating. E of P is this constant that's right here. Okay? And so when I go from black to blue, for the E of Q, I'm going to be always increasing because this V is always going to be inside this convex function. Okay? So I'm increasing for E of Q. but I'm going to keep it the same for E of P. Okay, so if I look at my objective, this is weakly increased. Okay, it's weakly increased because G of E of Q weakly increases, and G of E of P is constant, is the same, right, for blue and black. Everybody happy with that? Okay, I'm gonna go here. Okay, and the last part of this proof is that the extremal tangents are weakly less sloped. Okay, so we have this tangent here, which has to go from at most 0 to 1 to be bounded. We have this tangent here, which has to go from 0 to at most 0 to 1 to be bounded. And when I go to these tangents, oh goodness, what happens? My line is terrible. They're less sloped, right? Because the line from here to this point has to be at a lower slope than the line that goes, down following this convex function. Okay, so less extreme tangents, so they're weakly less sloped. So G bounded implies this V-shaped rule is bounded. Okay, so we take any G, which all scoring rules can be written in terms of G, and we say how to make it improve the incentive for effort, or the incentive for getting the signal by making it V-shaped. So the optimal scoring rule is V-shaped at the prior mean. Okay, and there's another note I want to give. Okay, so note. Okay, so in this mechanism, I get a signal, and so there's a distribution over my posterior mean that I get, right? If you look at this program, when I write it out like this and I write it V-shaped, right, it doesn't depend on it's not going to depend, if I optimize this, I just want to make it as big as possible subject to the constraint that, it's bounded. It's not going to depend on anything about the distribution except for the prior mean. The only thing I have to know is E of P. Okay, so for my class, I need to know that my mean grade is 80%. And I can tell you what the optimal scoring rule is. I don't need to know what the distribution over the student scores are.
So you also want the slopes to be as extreme as possible.
I will want the slopes to be as extreme as possible, subject to the boundedness constraint. Exactly, that's going to make my score bigger. So that's exactly like so now once I have it V-shaped, now the question is optimize it for V-shaped, and that's actually pretty easy to do. So I'm not going to write down any details of that. That's actually, I think, an exercise you're going to have this afternoon to figure out exactly what optimal V-shape looked like. This is not for binary. This is for a real valued estimate the mean. I didn't pay attention. What time did we go to?
12:30.
12:30, right?
Yeah,
Cool.
40 minutes.
And you can make this proper pretty easily by just making the line slightly convex.
You can make it strictly proper pretty easily by adding a little bit to it. But my philosophy of making it strictly proper by adding a little bit to it is if we didn't like the quadratic rule because we didn't think the incentives of quadratic were any good, which is strictly proper, then adding a little bit to this V-shape rule isn't going to do anything. It might be strictly proper, but the strictness is insignificant and so we shouldn't care. And so there should be no difference to us in deploying a scoring rule which is strictly proper versus not strictly proper if the strictness is not significant enough. Okay, and so my take is it's never significant enough. So you should never think about strict properness when you're optimizing scoring rules.
So does it help, like, how do you do multiple levels of effort?
That's a great question, Nicole. I look forward to reading your paper.
You said you did it already.
I tried to do it and I did not do very well. So I look forward to reading you doing a better job of it. A great idea.
Because you have convex optimization over set with the precision of belief. I think it makes sense.
Okay, which board am I on? This one. Yes, please.
So the input can be very complex, like it can be pi, it can be, it's mostly pi. Pi can be as rich as possible, and yet the optimal scoring rule is only uniquely defined by, the degeneracy is extremely high.
There's a lot of degeneracy, exactly. And one of the things that's interesting about this problem is that, like, compared to other mechanism design problems, usually you have to align the incentives of the agent with the principal to get the outcome the principal wants. But here I'm trying to maximize incentive for effort. If I fix the value that you get for the prior, right? Well, then everyone has the same thing. We just want you to get the most out of your signal. So actually our incentives are already kind of aligned, okay? And I think that's what's making it so that we don't care about all kinds of parts of the distribution because we're already on the same team here. We're trying to make your payoff for the information you have be as big as possible, subject to the constraint that the score for the prior is fixed.
And maybe a stupid question, but like, what's the minimal parameter to characterize the degeneracy basically here?
You guys can sort that out in the exercises. Good question. I'll let you sort it out.
Does it depend on the pi? I mean,
No,
yeah, it does,
no, it doesn't depend on
does
the
not
pi.
depend.
It
So
depends.
could
It depends only on E of P.
be E and P.
Which board am I on? This board. Yes, please.
So like if you say no, I care about, let's say, multidimensional data, are you going to get a code or something?
Great. So in this lecture, I only prepared the single dimensional stuff. In the paper that I mentioned that we wrote, we have a section on multidimensional scoring rules as well. This characterization of scoring rules for the mean also holds for multidimensional scoring rules. So if you have, if my homework had a rubric, and you are scoring, like, it's an algorithms homework, so you're scoring the algorithm, the proof of correctness, the clarity, like other kinds of things, different number for each one. That'd be like a multi-dimensional state. And so I would score each one, and the students would score each one. And then I'd want to understand, what do proper scoring rules look like? So the same characterization holds, where this is now the gradient. These are linear, these are now vectors, indicator vectors, right? And not indicator, for means they wouldn't be indicator vectors, but the same characterization holds. And then you can ask the same questions, and optimal scoring rules become a little bit more complex, but we showed how to define approximately optimal scoring rules that are get most of the value that are pretty good. And I guess the main punchline from that work on multi-dimensional state spaces and multi-dimensional scoring rules is the thing that everyone does is very far from optimal. The thing that everybody does with multi-dimensional states is use single dimensional scoring rules over each of the dimensions and then averages. Right? So like if I have a behavioral subject and I have them do a bunch of trials, right? And then a bunch of scoring rules in each trial, we average the score across the trials, or we sum them up and give you the total across the trials. So that takes my total amount of money and spreads out across all these decisions. So that does not maximize the incentive for collecting binary information. Okay, so you don't want to do that.
Because of correlation.
Not because of correlation, actually. Correlation does not matter. It's because what you want to do instead is, so that's like the average of separate scoring rules. What you want to do instead is the max of separate scoring rules. You want to let the agent have their posterior and pick which thing they think gives them the most, okay? Which, if you look at this V-shaped rule, is like, okay, on which dimension is your posterior furthest from the mean? That's where you get the most of your information. So in other words, instead of averaging the score you get across all the dimensions, I'm going to put all of my score on the one that gives you the most. Okay, and that's what you want to do with multi-dimensional scoring rules, but I don't have to, I'm going to talk about other stuff instead of that today. Yeah, but that's also good fun stuff. Yeah. Cool, let's talk about the maximum value from information. Okay, so I said at the beginning, we had a decision problem that I erased with the weather. We said, here's an information structure pi, and then the decision maker is going to play in this weather thing. And imagine we're thinking, oh, some machine learner is going to give us a prediction about the posterior. What is the probability of rain given a bunch of data, the label X, right? But we don't know what the decision maker's payoffs are going to be. Okay, so can we evaluate how useful this information is to our decision makers? Okay, and so I want to talk about the maximum value of information, because that's something that we now have the tools to talk about. And one thing I said was kind of annoying is the value of information depends on your decision. So I'd like to remove the decision and just have the value of information. Okay, so the maximum value for information is going to be basically the most useful the information can be. So I'm going to look at the decision that has bounded payoffs between 0 and 1, for which the information versus your prior, that difference is as big as possible. Okay, so I'm going to call the maximum value of information the expected difference of payoff with or without the information for the decision problem that's sort of best, that makes this difference as big as possible. Okay, and the result that now should be probably obvious to everyone is the maximum value of information is just the objective value of this program. Okay, and this is where the connection between proper scoring rules, which we optimized over, and all decision problems comes in. Okay, so this is the value of information is the expected difference with or without info for the best decision problem. Take that best decision problem, apply the revelation principle to it, you get a proper scoring rule. The optimal scoring rule from our program upper bounds the difference, the value of information for this decision problem. Okay, so it was sufficing to look at proper scoring rules to upper bound the value of any decision maker, even with a not proper decision problem. Okay, and so that's why we might want to look at proper scoring rules when understanding decision problems, even of a single decision maker. Cool. So why might this be useful? So if we're doing machine learning, we're trying to minimize our loss. We're trying to come up with predictions that have as small loss function as possible. Okay, so this framework lets us find the decision problem for which the loss is the greatest. Okay, that's going to look like a V-shaped rule. So in other words, most of machine learning looks at evaluating loss functions like squared loss. But how does having low squared loss relate to decision makers' payoff using this prediction? It's not clear how a particular squared loss will relate to a decision maker's payoff. The decision maker's payoff could be bigger or worse than this squared loss, right? But if we look at the loss according to the optimal decision problem that looks at the correct truth versus the prediction, so the truth versus the error, right? If you evaluate your error using a proper scoring rule, or the worst proper scoring rule, you will upper bound your loss of any decision maker. And so this kind of tools will get you, allow you to make claims about giving predictions to decision makers and upper bound the loss they face. Okay, so cool. And this is a property. This is a property just of an information structure now. I no longer have a decision problem because I've maximized over decision problems. I only just say this information structure, how good, like what's the most having the posterior over the prior could be. Cool. Any questions on that?
Can you repeat again what's the best decision problem?
Yes, I'm going to define the value of information by saying, find a decision problem that has bounded payoffs. Okay, so it's the U from my first slide, which I've now erased. Find a U, which maps actions and states to payoffs between 0 and 1. And I want you to find the U that makes having the information, having the signal, and knowing the joint distribution between signal and state, that makes having that signal as valuable as possible, meaning your payoff in expectation from your posterior in that decision problem is most bigger than your payoff and expectation with your prior in that decision problem. Okay? And the point is the program we just wrote down for that pi is going to upper bound this decision maker's payoff. In fact, it's going to be equal to the best, the most payoff the decision maker can get from your information. Okay, so for example, if you're wondering whether you should make some information available or not, and the best decision maker you can get from that information is not that much, maybe don't make it available. Maybe it's not worth it, right? And you can also use it for evaluating whether predictions are good as a loss function in machine learning.
So when CCF new Thursday, there will be some following.
I don't know too much. How much Bo is going to talk about that on Thursday.
CCF decision making using prediction from machine learning. Thursday.
Yeah, we'll be talking about very, very related stuff.
So it will be related to this somehow.
Yeah. But without as much amazing. one comment though, just so I guess if the mean is 0.5. Yeah, maybe ideas will come, but so if the mean is 0.5, maybe this value of information is proportional to the expected distance, right?
Yeah.
Because it's symmetric.
Yep.
It's kind of nice.
Yeah.
So, like, why would we be interested in maximum value of information and not expected value of information?
So the point is that basically we're saying we don't know what the decision maker, we have predictions, we have information, we don't know what the decision maker's problem is. Okay, so how much could this information be worth to the decision maker at its upper bound? That's maximizing the value of information.
It's basically we're looking at the soup part.
Yeah, I'm not sure. I mean, if we had loss functions, I would call it adversarial.
Oh, I see.
Right? But if for maximizing benefit, it's not, I mean, adversarial is not really the right word.
But here you are making an assumption about somehow the bound, we have some bounds here. You want the Elicit function, so g will be bounded by 1, let's say, until 1. So this assumption is somehow should be related to the bound in the
Yeah, exactly. So if I want to ask questions like, how much is information worth over all decision problems, I have to have some normalization.
Yeah.
And so I'm normalizing here ex post. I'm saying all scores got to be between 0 and 1. You could also try to normalize on average, and you'll get some interesting results that look similar to what I've been doing here. You can look at other normalizations, but you have to normalize. Otherwise, you can take a value of information of suppose I have a situation where my value of information is $1. Just scale all the payoffs by 1,000,000. Now the value of information is $1 million. Right, so it doesn't make sense to not normalize. All right, guess what? We are getting close to the end, and I have one more topic. Yeah, pi is fixed.
Just changing you.
Exactly. So when I say what's the value of information, I have to understand how that information distinguishes my posterior from my prior. That's given by pi. Yeah. So the question here is what properties of a distribution can be directly elicited? So a property, I have some notation for it. We'll say V. A property is a partition of the distribution. Okay, in other words, so distributions are all possible beliefs I could have over the outcomes. And I'm going to partition them into beliefs, distributions, where the property is the same. Okay, so for example, if my property is the mean, well, a point mass at 1/2 is a distribution. Mixing between 0 and 1 is a distribution. They have the same mean. Those are in the same partition. So all distributions that have the same mean will be in the same partition of distribution space. Okay, so in general, a property is going to partition distribution by the value of the property into the things with the same value. Okay, so it's basically this partition is the, what's it called? The level sets of the property. Okay, these are the distributions for which the property takes on the same value. Okay, so for example, properties we might care about are the mean. We've already been talking about that. The variance is a property of the distribution. Moments, like e of y to the k for some k. Things like mean cross variance, right? I can combine two properties and ask for both of them together, right? Which should be just the tuple of mean and variance. The mode. The mode is the element, if for a discrete distribution, like a discrete state space, is the element that has the highest probability. Those are all properties. Okay, and I want to ask which properties can be directly elicited, meaning there's a scoring rule that only asks for the property. So of course I can elicit every distribution with a proper scoring rule for the distribution and then compute the property. But that has me asking for extra information, right? And so we just saw the quadratic rule is in fact strictly proper for eliciting the mean, right? So we can directly elicit the mean of a real valued random variable. So now we're going to ask more generally, what properties can we directly elicit? Okay, and sometimes there are properties we can't directly elicit, but if we ask for a little bit of extra information, we can indirectly elicit that property. We'll talk about that too a little bit. Okay, so a property can be directly elicited if for all beliefs in my distribution over states, there's a strictly proper scoring rule. And so the property is the report that maximizes the score given the report and my belief. Okay, and again, my belief is over the full distribution. I'm drawing y from my full belief, but I only want to just report the property.
If there is strictly scoring rule S,
I'm going to write this.
for all P there is, so this means that the scoring rule depends on P?
No.
So it should be if it depends on P. If there is a
Yeah,
score-
you're saying I want this statement here.
Yeah.
That's correct. Sorry.
And the scoring rule inputs R is in this is in delta phi or is
Property
in
space.
Property space. Property space.
Okay, so the only lemma I'm going to prove here, I'll state the theorem, which we'll get to next, but I want to prove this lemma because I think it really provides a lot of intuition, is that elicitability implies convexity. Okay, in other words, the contrapositive non-convexity means non-elicitability. You cannot elicit directly non-convex properties. Convexity of level sets. Okay, you cannot elicit properties where the level sets, okay, in other words, the sets where you have the same value of the property are not convex. Okay, so the level sets need to partition the space of all, the simplex, the space of all distributions, into convex regions where you report the same amount. Okay. Okay, e.g., we already know the mean is elicitable. Okay, and let me just say what this means for the mean. If I want to say the level sets are convex. Take any two distributions with the same mean. Mix over them. That new distribution you get from mixing over these two distributions also has the same mean. Right? Like I take my distributions of point mass on 1/2, I take my distribution that's 0 with probably 1/2 and 1 with probably 1/2, I mix over these. Okay, good. So I get 0 with probably 1/4, 1 with probably 1/4, and 1/2 with probably 1/2. That also has mean 1/2. So the level sets of the mean are convex. Okay, so it satisfies convexity. Oh, we already know that it's elicitable from the quadratic scoring rule, so good. Okay?
Do we mean by level sets exactly T or at most T?
What's T?
Like the level, like, okay, what's a level set?
The level set's the exact value.
Exact value.
Exact value.
Variance is not elicitable. If I take two distributions with the same variance and I mix over them, I don't get a distribution with the same variance. Okay, so cool. Mean, yes. Variance, no. What about moments? Yes. Someone tell me why. Variance is the mean with a change of variables. variance, sorry, I said moments, right? So mean, yes, variance, no. What about moments?
No.
The answer is yes. Moments, yes. Why? Because moments are just means with a change of variable. So the mean of y to the k, I can elicit because I can elicit the mean. Okay? So the same scoring rule I use to elicit means, I can use to elicit the moments just by plugging in y to the k as my truth. Okay?
What about sum of two things that are illicit? Sum of two functionals that are illicit.
If I have two things that I can elicit it the combination of the two things. The sum of the two things, I don't know. You can figure that out.
In this case, like,
What about mean and variance?
no.
I mean, if you ask for two information, you can, right? If you ask for the
No, I want to directly elicit just the mean and just the variance. Huh?
Together.
Yes, together. Can I do it or not?
Variance, no, it's no.
Like the mean and the second moment, right?
If you elicit the mean in the second moment, you can compute the variance, and you can elicit both the mean in the second moment. So you can compute, so you can elicit this. So this is yes. Our moments are yes, and mean and variance is yes.
So in what sense is variance no?
Yeah, exactly. That's what.
You can't directly elicit it. You have to also ask for the mean if I want to compute it. Yeah, the main word here is directly. I only ask for that. I don't ask for S for information. Remember, if I'm going to ask for S for information, I just ask for the full distribution, everything I can compute. Okay? I can elicit the full distribution. I can compute any statistic.
That's not clear for us.
That's why we do the examples. Now it's clear. All right, you guys happy? How are we doing? 10 minutes? I can do this proof in 10 minutes.
About the definition of directly elicitable. So you can choose your scoring rule
Yeah. The scoring rule you get to pick.
and the report.
Huh?
The report. So R lives in a. First it was the full distribution. Now it's a number. You can the space of.
The report space is a space of properties.
And you can choose.
The point is that for the mean, it's like just all values the mean could take on.
Do we have some way to recover elicitability from convexity, like convexity plus something else, maybe, or like what do we need to?
I'm going to give you a characterization of what's elicitable properties in a second.
Okay.
Right now, I'm going to prove this lemma, which is not a characterization. It's necessary for it to have convex level sets, but not sufficient. Okay, but I like this proof of the lemma because it comes back to something that someone said before.
expectation of the max bigger than maximum expectation.
Yes. Okay. Thank you. Yeah, no, that's perfect. If Okay, so I'm going to restate your comment in the following way. If the optimal report to make with information is the same across all information you could have, then it's also optimal without the information. Right? In other words, imagine it was the case that the optimal thing to do if it was rainy or cloudy was not take an umbrella. Okay? Well, then the optimal thing to do for any distribution over rainy or cloudy, sorry, I misspoke. If the optimal thing to do for cloudy or not cloudy is to take an umbrella for your payoff function for u, right? Then the optimal thing to do for any distribution over cloudy or not cloudy is to take an umbrella. Okay, so if you have the same answer without the information, sorry, for every information you could have, you get the same choice, then you have the same choice for any distribution over that information. Okay, so that basically, and then convexity. Okay, why are we basically done from this observation? Okay, consider two beliefs that have the same statistic. Okay, if I have a proper scoring rule for that statistic, you should report the same number. So the optimizer of my scoring rule for both these beliefs is the same optimizer. Any distribution over these beliefs has to also have the same optimizer in my scoring rule. Okay? But the optimizer of my scoring rule by strict convexity has to be my statistic. So the statistic has to be convex, because any point in the convex combination of the two distributions has the same statistic value. I'm not going to write that, because I see I have 4 minutes left. And this is the key fact, and you guys can figure it out from that if I don't write it, right? Cool. So I'm not going to write it.
This is the same argument used to prove that you have calculation of probability equilibrium from the general definition of Oman?
I don't know. But it is the same argument that's used in other places in mechanism design to solve mechanism problems where you relax some constraints, you solve the relaxed problem. If you get the same optimal solution for all those relaxed problems, then the solution is the solution for the original problem. So you do something like you take your incentive constraints, you relax some of them, you solve. You get the same answer then without the constraints, then it's good.
Canonical correlative equilibrium is kind of mechanism design problem. The mechanism that tells you should report the truth. Be a correlative equilibrium.
Okay, so here's the characterization of what statistics are directly elicitable. A statistic is directly elicitable if and only if the level sets are the intersection of a Voronoi diagram on basically if y is states 1 through k, then this is like a vector, real value vector with k possibilities. And belief space where this is the simplex on the k possibilities. Okay, this looks a little bit confusing, the intersection of this with this. What does that mean? It's basically a generalization of Voronoi diagrams where the centers don't have to be in the same space as the space we care about. Okay, so if we were drawing the simplex on outcomes A, B, and C, okay, there could be centers in the plane, basically, off the plane, right? And a Voronoi diagram is the regions you get where you take the closest point to every center in Euclidean space.
Do I count these points?
Okay, so for example, this statistic where I want you to say, you know, A, B, C, D here, that's elicitable because there's a Voronoi diagram that gives this. Here's an example that's not elicitable. You cannot make a straight line with a, you know, any line coming into it like this or like this. Like that can't happen. So you cannot elicit this. So for example, some decision trees are not elicitable. So the decision tree, like here it would be A, B, C. So I want to say A, you know, with probably 50%, or the better of, you know, the more likely of B or C. Right, so you've got a belief, which is in the simplex. Okay, and so what I want you to do is say A if it's more likely to be A. So 50% of A, which is, you know, this line where this is 50%. Right, and then I want to say the more likely of B or C. That'd be a decision tree, you know, where this is now 50%. Not elicitable.
When you have Bernoulli diagram, you expect the Euclidean distance
Huh?
to complete them.
Euclidean distance.
How do you count the Euclidean distance if you don't have any geometry?
I think if you want other distances, you can simulate them by putting the points outside the plane, outside the space you're in. This is what this intersection with Ry is. It's a cool result. This is a paper by Nicholas Lambert.
Perhaps you have this Euclidean distance coming from the geometry of convexity, probably, or something like that.
Yeah, so here's the thing. We know that for it to be proper, I had this on a slide somewhere, but there's got to be some convex function G, right? And the score is the supporting hyperplanes of this convex function G. So if it's a statistic, if you're getting the same score for a bunch of reports, that's got to be faces. This convex function G better have faces, okay? So this characterization is just saying, what do, if I take the simplex and I put a convex function over the simplex, and I say, how can I make it be piecewise linear? What's it going to look like? It's going to look like a Voronoi diagram over belief space, you know, this intersection. That's what it looks like when you project it down into the belief space.
It's important that basically between two distinct sets, the separation is linear. That's what.
So to not have it. So like if I had a line like this, but oh, sorry, yes. And also the line between two sets has to also be linear. Yeah, yeah. So between any two sets, it's got to be linear in belief space. And you can't have this kind of a thing.
Vertical and horizontal is almost elicitable, right? If you
Yeah, yeah. So you can. So if you want to like almost elicit it, you could elicit this. Yeah. A very good point. That center is going to be like way out here.
So for this almost elicitability, like we have like control on the error between what they would the score they would get.
Yeah. So how would I elicit? So suppose I gave you a Voronoi diagram, and I said, and how would you elicit it? Easy, right? I only let you report the Voronoi centers, and I use squared error to penalize you. And so if I only let you report the squared errors, then whatever your belief is, you're going to choose the center that's closest to you, the Voronoi center that's closest to you.
But if the centers are not in the distribution, they're outside.
That's fine. It's still the closest one.
The nearest neighbor.
Okay.
You have to report a non-distribution, but you still want to report the closest one. I am 5 minutes over. I'm going to want to stop here. The things I didn't write, I have a couple more things in my notes. I also have all the references for the stuff in my notes, which hopefully, was it emailed to you guys? Perfect. So you guys have my notes, and you've got the references, and you've got the last little bit. The only thing I want to say in the last little bit is I talked really about mostly optimizing scoring rules for the mean. And there we use the characterization of proper scoring rules for the mean. You might want to optimize scoring rules for general distributions. And actually, it's the same characterization, but it's easier. There's no kappa. Right? The kappa comes because of this multiplicity. There are multiple distributions with the same mean. And so you have to add this kappa term. If you are reporting the full distribution, there isn't a multiplicity. And so you don't need the kappa. So it's just, there's a function g, it's a convex function over belief space written multidimensional over the simplex. That characterization is identical to Roche's characterization of multidimensional incentive compatibility for mechanism design. Okay, so McCarthy 56 proved the exact same theorem as Roche in Econometrica 85. Okay, those are the same theorems. And so if you want to think about optimizing scoring rules, and you know a whole lot about doing mechanism design, all those tools can be brought in to optimize scoring rules. The big difference between optimizing scoring rules and doing mechanism design is usually in mechanism design we care about things like revenue or welfare or other things like that. And in scoring rules we care about things like accuracy or incentive for getting information or these other objectives. So I think there's a whole host of open, interesting questions thinking about optimizing scoring rules for different objectives you might have. And this is sort of maybe the beginning of looking at what scoring rules are good for various tasks. So with that, thank you so much for your attention.